Hi, Transitional Math students. Let's go ahead and work Practice Benchmark Chapter 11 and go through these problems. All right, the first problem gives you this figure. You have two parallel lines cut by a transversal, and when that happens, you have all kinds of congruency that occurs. So one type of congruency is alternate interior angles, which means they're on the inside of the parallel lines. So these four are on the inside of the parallel lines and they're alternating. So 3 and 5 would be congruent, also 4 and 8. Alternating exterior angles are also congruent. So these two are on the outside of the parallel lines, also these two. The alternate exterior would be 6 and 2 or 7 and 1. Those are congruent. Also, corresponding angles are congruent. Angles that are in the same spot on the same side of one of the parallel lines. So angle 8 is on the left of this parallel line, and angle 2 also on this side of the transversal. So 2 and 8 would be congruent. Also, for that same reason, 1 and 5 would be congruent. Or 3 is on the right-hand side of this parallel line and 7. So 3 and 7 would be congruent, or 4 and 6. Another thing that occurs is vertical angles are congruent. 8 and 6 are congruent, 5 and 7, 2 and 4, 1 and 3. Those are vertical angles. So knowing that, let's go ahead and answer these questions. They give us the measure of angle 5 is 128. Then they ask us to find the measure of angle 2. Well, measure of angle 5 is inside, and the measure of angle 2 is outside. It would be nice if there are alternate interiors or maybe alternate exteriors, then they would be congruent, but they're not. However, I know 2 and 6 are congruent because they're alternate exteriors. And I can figure out the measure of angle 6 because this makes a straight line. Anytime you have a straight line and two angles sharing it, that means they're supplementary or they add up to be 180. So I'm just going to go 180 minus 128. And what's that going to give me? 52. So I know angle 6 is 52 degrees. These two add up to be a full line. 180 degrees is a full line. And I know angle 6 is congruent to angle 2. So if 6 is congruent to 2, I know that angle 2 is also 52 degrees. All right, on to number 2. Okay, so number 2, we're using the same picture, these same parallel lines. They tell us the measure of angle 6, here's angle 6, it's 3x minus 13. That's a 13. Let me try that again. Okay, and then the measure of angle 8, this angle right here, is 2x minus 5. Okay. Now I can see angle 8 and angle 6 are vertical angles. When you have two angles that are vertical angles, they share a vertex and two sides that are intersecting makes them vertical angles. They are congruent. So all I need to do is do this. 3x minus 13 is equal to 2x minus 5. Now I've set it an equation, so now I can solve for x. Easy peasy. Let's get all the x's together on one side. I like to pick on the smaller number, which is 2 x's, and I bring them over here to this side. 3 x's minus 2 x's is just 1x. Bring down the negative 13, bring down the equal sign, that's 0, and then bring down the negative 5. Now I need to solve for x, so I want to isolate it. I got to get rid of this minus 13, and the opposite of minus is add. So I add 13 to both sides. That eliminates that. Bring down the x, bring down the equals, and negative 5 plus 13 is the same as 13 minus 5, which is 8. So the value of x is 8, or C. All right, the measures of the angles of a triangle are in this ratio, 3 to 4, or excuse me, 4 to 5 to 9. What are the angle measures of the triangle? Well, any triangle, I mean, I don't know what this triangle is, but any triangle, all the interior angles of a triangle add up to be 180 degrees. And this has been the ratio of the triangle. So there's some value here. I don't know what the value is, but it's been reduced to 4 to 5 to 9. So let's say that value is x. 4 times that value of x plus 5 times that value of x plus 9 times that value of x has to be 180. This is the ratio of the angles. And I have some value for the angles. So if I have that ratio and I reduce it to 4 to 5 to 9, I want to know what it was before I reduced it. Well, let's figure out what that value of x was that they could factor out to reduce. So I just give it a value of x. I know this angle plus this angle plus this angle has to be 180. So I just go 4x plus 5x plus 9x has to be 180. And then I figure out what that x was. So let's go ahead and add these together. 5 plus 4 is 9, and 9 plus 9 is 18. So this is 18 x's equals 180. And then divide by 18. And you're going to end up with x equals 180 divided by 18 is 10. So you know that value was 10. That's the value they factored out of here. So that means 4 times 10, this angle had to have been 40. 5 times 10, this angle had to have been 50, and 9 times 10, this angle was 90. So this was actually a right triangle because you have a 90-degree angle, so I didn't even draw it correctly. It was a right triangle, or I could have maybe made this a right angle here, maybe something like this, where that was your right angle, maybe. All right, so there's your 90, and then you would have a 40 and a 50. So I'm going to go 50 here and 40 here. And that's what my triangle was. So 40, 50, 90 was the measures of the angles. So anytime you have a ratio and you're trying to find out the angle measures, take that ratio, multiply it by a value of x, and set it equal to 180. On that same lines, let's look at the next one. The measures of the angles of the triangle, once again, are in a ratio of 3 to 4 to 5. It says classify the triangle. Now we can classify the triangle in 3 ways. We can have the sides and the angles. Okay, sides, we would classify it as scalene, S-C-A-L-E-N-E, isosceles. So scalene, all the sides are different lengths. Isosceles, meaning 2 sides are the same, or equilateral, meaning all 3 sides are the same. Okay. Now the angles, I can classify it in a triangle that is acute. It could be right. Now acute would mean all the angles are less than 90. Right would mean one angle is 90. Or obtuse. Obtuse would mean one angle is greater. Let's see. Let's write it like this, and I'm just sketching this out, greater than 90. Okay, so acute, right, or obtuse. Now, they give us a ratio. I can figure out the measures of the angles because they give us a ratio just like here. This is reduced from what it originally was of the angles. So I'm going to do this. 3 times whatever that number we reduced out, plus 4 times that same number we pulled out, plus 5 times that same number. That, when I add up, must be 180 because they said these were the angles. So when I add these guys up, I'm going to go 3 plus 4 plus 5, and add all these up, I'm going to get 12x equals 180. And then divide by 12. And then x is going to be, I'm going to write it over here because this is down here. 180, if I do 180 divided by 12, I get 15. Now when I do this, x is 15. Let's go figure out what was the measure of the angles. Well, 3 times 15 is 45. So one of the angles is 45. 4 times 15 is 60 degrees. 5 times 15 is 75 degrees. And when I add these all up, they do equal 180. Now let's figure out, based on the angles, I don't have any angle that's bigger than 90, so it's not obtuse. I don't have a 90-degree angle, so it's not right. It has to be acute. They're all less than 90. So I know I have an acute angle. Now with the sides, if each of these angles are different measures, all the sides have to be different measures because we just have a little rule with triangles. If it was an isosceles triangle, meaning two of the sides were the same length, that would mean the angles would have to be the same length. And if I do 60, actually all angles will be the same. 60, 60, 60 makes 180. But if two of the angles, the side opposite will match up with the angle. So if two of the sides are the same, two of the angles will be the same. If they all have different measures, I'm going to have a scalene triangle. If two of the angles had the same measure, I would have isosceles. If all three angles had the same measure, meaning they're all 60, I would have equilateral. So this has to be acute scalene. I actually looked at the answer key and they said it was a right triangle and it was scalene, and that's not correct. And I'm believing it's because they looked at this initially and go 3, 4, 5. If those were the lengths of the sides of a triangle, the side lengths 3, 4, 5, then you would have a right triangle based on Pythagorean theorem. Okay. If this was a 3, 4, 5 for the side lengths, you would have to have a right triangle because 3 squared plus 4 squared equals 5 squared. So I fixed that on the answer key. It has to be this one because they were talking about angles, not sides. All right. We're going to classify this polygon just by its sides. It looks like a regular polygon. It looks like all the sides are the same, but they just want to know the number of sides. So I'm going to go, there's 1, 2, 3, 4, 5, 6 sides. A pentagon is 5 sides. This is 8 sides. 7 sides. Hexagon is 6 sides. All right, find the sum of the measures of the interior angles of a polygon with 6 sides. Not the exteriors, but the interior angles. And there's a rule. N minus 2 times 180 gives you the sum of the interior angles of any polygon. It even works with triangles. You know that triangles add up to be 180. Also, any kind of quadrilateral is going to be 360, but it works for them. With triangles, there's 3 sides. So you would go 3 for the number of sides minus 2 times 180. Well, 3 minus 2 is 1, and 1 times 180 is 180. 4 sides, you would go 4 minus 2 times 180. Well, 4 minus 2 is 2, and 2 times 180 is 360. So it works even for the ones you already know. The ones you don't know, say the hexagon, it has 6 sides. You would go 6 minus 2, and then multiply that by 180. Well, 6 minus 2 is 4. So you're going to go 4 times 180, and 4 times 180 is 720. So it's B. Just know that the measure of the interior angles of a polygon is the number of sides minus 2 times 180. All right, we're going to move on to translations. You got a triangle and it has these vertices. The vertices of the image are here. Which statement describes this transformation? Now you can draw out a picture, which I always suggest. I'm just going to pull up, let me pull up a little graph paper right here. Hold up. Okay, so if I were to graph these on a little coordinate plane or some graph paper, X, you would go over 6, 1, 2, 3, 4, 5, 6, up 0. So there's your X. Y, you go over 4, 1, 2, 3, 4, and down 4. 1, 2, 3. There we go. There's Y. And then Z, you're going to go over, if this is 6, this is 7, this is 8, and down 4. So there's Z. And there's my triangle. Now I want to reflect this triangle over, let's see, let me draw that. Okay, let me reread the problem. Which statement describes this transformation? Okay, well, let's see what the transformation was. Let's do it in blue. So X prime is that same spot right there. X and X prime are the same. Y is over 4, 1, 2, 3, 4, and up 4, 1, 2, 3, 4. There's Y prime. And then Z is over 8, up 4. There's Z. or z prime. And that was a really big scribble. Let me try that again. Is that 8? 1, 2, 3, 4, 5, 6, 7. Yeah, up 4. So there's z prime. Now if you look at this, it looks like the triangle has been reflected over the x-axis. Here's the x-axis, here's the y-axis. It looks like I just flipped it. So I'm going to go with, just based on graphing it out, and I just moved the graph, sorry, a reflection over the x-axis. That's what I'm going to go with. And D. So it helps just to graph it. Now you can kind of see, if you look, when you reflect over the x-axis, your y values change. So if you look, the x value is the same and the y value reflects. Well, 0 is just 0. The x value here is the same and the y value reflects from 4 to -4. The x value here is the same and the y value reflects. So the x stays the same. You go over on the x the same. It's the y that reflects. When you're reflecting over the x-axis, that's what happens. All right, let's go ahead to number 8. Let's see. Find the coordinates of C prime if triangle ABC shown on the coordinate plane is reflected over the y-axis. So I want to reflect over the y-axis here. Here's my y-axis right here. That means I'm going to reflect over it. And I have C. If I want to reflect over the y-axis, I go perpendicular to the y-axis. I count that number of coordinates. 1, 2. And then I do that same number on the other side of the y-axis perpendicular. 1, 2. And I land right there. There's my C prime. So that's where I would place my C after reflecting it over the y-axis. Now what are those coordinates? The coordinates are over 2, down 1. Over 2, down 1. So C prime would be over 2, down 1. It would be A. All right, on to the next one. Okay, this one's probably the trickiest one when you're doing rotations. It's easier when you do rotations around the origin, but when you're doing rotations around a point, it's a little trickier. So I would like you to graph this on some kind of graph paper. You're going to go over 2, up 0 for t, so there's your original t, over 1, down 2, and I'm actually going to make this a little bit bigger. Let me see if I can make this bigger. Hold on. Okay. A little bigger. All right. Just so we can see it better. Let's do those points again. Hold up. I've graphed over 2 up 0 for t, over 1 down 2 for u, and then over 2 up, or sorry, over 1 down 2 for u, and then over 2 up 1. I put u there again. Sorry, I meant z. For z. All right, so there's my points. This is a triangle, so I'm going to go ahead and connect the dots and make this be a nice triangle here. So go ahead and draw out your picture nicely on some graph paper. Now, in order to rotate this 90 degrees clockwise about the vertex z, I really want to have one of these, okay, a protractor. This will help me, and a compass, but if you want to just guesstimate by drawing, 90 degrees is an L. So if I were to make an L from, and I'm going to rotate around point Z. So if I want T to rotate clockwise, meaning this way, around point Z, so I'm going to have it go this way 90 degrees. I'm going to draw that 90 degrees. And that was a little sketchy. Let me draw a straight line here. Okay. So if I were to go from this straight line over to here, this would be 90 degrees. This is an L. Okay. I'm going to rotate this up 90 degrees and I'm going to keep this length the same. So I'm going to take this right here, this value t, and I'm going to rotate it 90 degrees and land right there. All right. I'm going to erase that extra long line I had there. Now there is my rotation for T 90 degrees. From here to here it went 90 degrees. And there is my new T. This will be, oh, I keep erasing. Hold on, sorry. Let me put back my T. All right. There is my rotation 90 degrees. And this will be T prime right here. All right. What are the coordinates of U? Now U is a little harder. So from here to here, from Z to U, I want to rotate this 90 degrees. So what I'm going to do is draw a little line, and I'll draw it in red from here to here. Okay, and then I'm going to rotate that 90 degrees. So I want to make an L there. There's my L. Okay, that would be my 90-degree L. Do you see that L for these two right here? Now this length right here needs to be the length I bring over here. So I'm going to take that length and I'm going to replicate it over here. Okay. Hold on. Did I keep it the same? Hold on. Okay, let me just draw that again. I missed it. Okay, here's I rotated T 90 degrees. Now I'm just gonna go ahead and pull this over again. Sorry. From U to Z, there is that, and I want it to be 90 degrees. So I'm gonna try to make an L here, like this. All right. Let me see. And I'm guesstimating right there. Okay. Now I want this length right here to be, there we go, to be about the same length as, or exactly the same length as it was, if I can keep it that length as I pull it. There's that length right there. So I'm going to erase what I had there before, erase that other one. And there's the length I have right there. So pulling this length over to here, here is a 90-degree rotation. See that L right there for U to here. So this will be my U prime. This was my T prime. There's my U prime right here. And if I want to connect this back, there will be my rotation from here to here. And that was ugly because I drew it by hand or by freehand, but I rotated this triangle to here. Now what's that point? It asks for U prime. Let's see, that point would be -1 up 2. So -1 up 2, it would be B. All right, that's the trickiest one when you have to rotate about a point. So just real quickly to go over that again. When you're going 90 degrees, you first take about a point, you go from that point, and then you pull it 90 degrees. There's your T. And then from U to Z, there's that point, and we want to pull that. There's that point, and we want to pull that. So it's 90 degrees. So it makes that L. And that gives us the U point. All right, that is a tricky one. Okay, on to the number 10. Okay, triangle QRS has vertices 0, 0, 2, 0, and 2, 3. The triangle is translated up 3 units, then it's reflected across the y-axis. So you would go up 3 if this is x and y. If you had any point, let's say the point 2, 0, there's R. You would go up 3 and then you would reflect across the y-axis, okay? Here's the vertices of the image. Which statement explains why the two triangles are congruent? All right, both triangles have right angles. Well, just because they have right angles doesn't mean they're congruent. The side lengths are the same measures. Well, you could say that let me see. If all the side lengths have the same measures, would that mean the triangles are congruent? Actually, it does, because that would be side, side, side. But let's see why for the translation it would mean they're congruent. The ratios of the side lengths are greater than 1. Translations followed by reflections preserve shape and size. This is very true. We did a translation and a reflection, but we did not change the size or the shape of our triangle. This is why the two triangles are congruent. D. Okay, side lengths are the same measures. That's true, but that's not why these two triangles are congruent. We took the triangle, we shifted it up and reflected it over, but it keeps its shape and size, so it's congruent. Okay, these two triangles are similar. They told us they're similar. Okay, so we don't have to check the ratios of the sides. They said they're similar. Which series of transformations maps ABC onto DEF? So I need to get from here to here. Now I can see to get from here to here, I would have to move it over. So I'd have to do a translation to the right. And then to get from here to here, I would have to blow it up a bit. If these are ratios, 9 to 13.5 is the same as 3 to 4.5, I would have to multiply it, or I'd have to dilate it, make it bigger. So let's see, I need a translation followed by a dilation. Let's see, reflection, rotation, translation, followed by a dilation. So it would be C. All right, let's go on to number 12. Number 12 asks, determine whether the figure shown has rotational symmetry. If it does, describe the angle of rotation. So looking at this, I can see if I rotate this to here, or this to here, or this to here, it's not going to change this picture. It's going to look identical. So yes, it does have rotational symmetry. So I'm going to say yes. The picture doesn't change, all right? What is the angle of rotation where the symmetry exists? Well, look, if I take this from here to here, that's 90 degrees. And I don't need to go that far. I can just go from here to here. That's half of 90. Half of 90 is 45 degrees. 45 plus 45 makes 90. So what is the angle of rotation? It's 45 degrees. All right, on to the next one. Okay, we're going to let P, -6, 4, be a point on this rectangle. What are the coordinates of P prime? So the image, if the rectangle is dilated by a scale factor of 2, if it's blown up by a scale factor of 2, that means I have to multiply each of my lengths by 2. So I'm just going to take each of my coordinate points and multiply it by 2. It's simple as that. So I'm going to say -6 times 2 is -12, and 4 times 2 is 8. So if I dilate it by a factor of 2, I would get the point P prime, which would be -12, 8. All right, let's go on to the last one. Charlotte is creating a triangular pennant with geometry software. So I'm just going to draw a little triangle here to represent this pennant. All right, I don't know exactly what it's like. The base measure of the pennant on screen is 550 pixels. So let's go. The base measure is 550 pixels. The height is 275. So let's just make this be our height just to represent it and get a picture of what we're dealing with. 275 for the height. All right. Charlotte resizes the pennant, keeping the aspect ratio constant. So they're going to be similar, right? So the height is 165 pixels. So her new pennant, she wants it to be smaller. And let's not do that. Let's do this. She wants it to be smaller, not quite so big, right? She'd like it to be smaller. And she wants the new height, and I didn't draw that very good, but that's okay. The new height to be 165 pixels. What is the scale factor of the dilation, and what's the base? So the base we don't know, right? We want to know the scale factor. Now, if she's keeping the aspect ratio the same, the scale factor we would just set up like this. 165 divided by 275. Okay, so that scale factor, go ahead and divide that out on a calculator. If you go 165 divided by 275, you're going to get 0.6, all right? So 0.6 is going to be the scale factor, 0.6, and you can do 0.6. That equals the scale factor. Now you can use that scale factor to figure out what this is. If I take 275 and I multiply it by 0.6, I'm going to get 165. Okay. A lot of students will want to go 275 and divide it by 165, but if I did that, if I divided this by this, and then I multiply it, that would give me, if I do 275, let's just do it. 275 divided by 165, I'm going to get 1.66. If I take 275 and I multiply it by 1.66, I don't get 165. I need to multiply it by 0.6. You're undoing it, okay? So 165 divided by 275, there's our scale factor. Take this one divided by this one. Now to figure this out, well, to get from here to here, I multiplied by 0.6. I got smaller, okay? To get from here to here, I just multiply by 0.6. So we'll go 550 times 0.6, and you're going to get 330. So what is the base of the pennant? 330 pixels. If you like to do ratios, another thing you could have done 165 over 275. Okay, so small to big, and then you would go small base to big base. That would equal small to big. And then you would cross multiply and divide. 165 times 550, that's going to be a big number. 90750 equals, and then this times this would be 275x. And then you would divide both sides by 275. And you would end up with x equals, and I am not looking while I'm writing, sorry. X equals 330, which is the same that we got by using the scale factor. So you could do it this way. All right, guys, that's it for this test. Good luck, and let me know if you have any questions. Have a great day.